Good morning, everyone in the room and remotely connected. Do you have any question? There is a micro open. If you could please silence it. Okay, I silenced it. Good. Okay, so let's move forward with the next link, model calibration and validation. I think, let me see if there is a PPT. No, but this is quite simple. We already introduced this topic during our last exercise. I want to discuss with you now the issue of parameter calibration, parameter estimation for models. And I deliberately say models because the subject has a general, makes reference to a general context, and what I am discussing today is basically applicable to any parametric model. Of course, we make a specific reference to water resources models, but any parametric model that is used, for instance, to simulate environmental processes, but I could say also in general any type of process. Any parametric model has to undergo an essential step that is parameter estimation. So to find the best values for the parameters. We can call this procedure also parameter calibration, parameter optimization, or model optimization. These are synonyms. So just get used to these different terms with the same meaning, which means that we have to find, as I said, the best values for model parameters. When we did the exercise last Thursday, we already made the first experiment of parameter estimation. We did it by trial and error. But then I also said that this procedure, when we have several parameters to estimate, is a bit demanding, a bit complicated for the several trials that we have to make. And therefore, I mentioned that a possible solution to simplify the problem is automatic calibration. And this is already making a first difference between two main categories of procedures that can be used for parameter estimation. And these are trial and error procedures and automatic calibration procedures. And these are both part of a more general category of approaches, which are the approaches that are based on the optimization of model performances. So we decide for a performance measure, which can be a visual evaluation. So it's a kind of subjective performance measure. I make a visual evaluation of the goodness of the fit, like in this case you see on the screen an hydrograph, an observed and simulated hydrograph, and I make a visual assessment which brings me to conclude that the simulation is acceptable and therefore the parameter values are acceptable. Or otherwise, we introduce for automatic calibration a quantitative performance measure. So this is, as I said, calibration through optimization of model performances, which we can split in trial and error procedures and automatic calibration. We already discussed briefly the pros and cons of these two categories. We said that the visual assessment gives the benefit, the advantage of allowing a comprehensive assessment of the goodness of the fit. So by looking at observed and simulated hydrographs, I can get a overall assessment, a comprehensive assessment. So I could say, for instance, that the high flows here are well simulated, but we can see here that the timing is not really perfect. So the simulated flow is anticipated a little bit. So this is a possibility that is given by the visual comparison. I can say, good, the peak is well estimated, the timing is not perfect, the low flows are not so good. Of course, if we introduce a quantitative assessment through a number and we use the least squares in our experiment on Thursday, this number gives us only an overall indication. It doesn't allow us to get the details, like peak is fine, timing is not fine. The number, the least square measure, only gives, say, yes or no, basically. And it's not giving much details. So the visual comparison from a technical point of view is preferable. And this is a pros of the visual assessment. On the other hand, we said that the disadvantage of the visual assessment is that it takes a lot of time. Even if I make an automatic calibration and I ask the program to show me the graph at each iteration, which we did on Thursday, of course, this procedure, as I said, slows down the optimization a lot. And therefore, this is a considerable disadvantage. Keep in mind that some models take a lot of time to run. In our case, iMod was very quick, but it may happen very easily that each model run takes 5 minutes. So if you have to make a lot of trials, you understand that it may be a long procedure that you need to simplify, you need to speed up. So we discussed already these two pros and cons, disadvantages and disadvantages. And now let's go into the details into more details regarding the objective function that we can use. What is the objective function? It is the performance measure that we use in automatic calibration. This performance measure can assume different forms. On Thursday, we used, as I said, the least squares performance measure. Basically, what we did is to compute the difference between observed and simulated data. We squared it in order to avoid, as I said, compensation between positive and negative errors. And then we took the sum of the squared differences as an integral measure of the model performance. Okay, this is what we did. And actually, I already mentioned to you that this is a performance measure that is widely used. Let me magnify on the screen this equation. This is what we used. So if we indicate with xt the observed values and with the x at t the simulated values, the at stays for simulated, estimated. Then we compute the difference, we square it, and then we sum over the whole sample, which has size n, of our data set. Very good. And this is called, as I said, least squares performance measure. You may remember that I emphasized that by squaring the error, we put more emphasis on the high flows. Because with the high flows, we make the highest errors. And therefore, if I square a large error, of course, I get a very significant weight of this large error in the whole summation, in the whole objective function. And so I said, this is it's a good solution, but on the other hand, in water resources management, I am often interested in the simulation of low flows. And therefore, if I am interested in the simulation of low flows, this performance measure is not really the best one that I can use. This performance measure has a large popularity, and there is a reason for that. The reason is that we can prove under certain conditions, under certain assumptions that we don't expect. We are not interested in that. But it can be proved that this performance measure for n that tends to infinity gives what we say an asymptotically because n is tending to infinity, consistent and unbiased estimator, which means that in poor words, for increasing n, you converge to the true solution. Okay? Asymptotically consistent means that we converge to the true solution. Unbiased means that the errors that you make in the estimation have an average of 0. So, I mean, this is a good behavior that we appreciate, because this is what we want. We want that for increasing availability of observed data, we have an estimator that is performing well. It converges to the true solution. This is not always true. You may use estimators that, even for large n, don't converge to the true solution. So, but we don't go into the details of these statistical behaviors. I just wanted to tell you that there is also a theoretical reason why this objective function is widely used. And also this consideration that I just made, the fact that this estimator is a good estimator, is an estimator with good performances, should alert you on the fact that when you optimize a model, when you estimate parameters for a model, you have to be concerned about using a method that is a good method, that brings you towards the good solution. I mean, if you have uncertainty because you have a limited number of observations available, this is not a big problem, as long as you use a method that, under the assumption that you have a large n, this method is good. And this is something you have to be concerned about, because, when you calibrate models, you often use, especially in the trial and error procedure, some judgment that is subjective, and it may be, at the end of the story, it may be not a good method for parameter estimation. This consideration alerts you that there is also a theory behind it. And it's a theory that assures you that you are using the correct one. So this one, there is a theory behind it under certain assumptions, I said, which we don't expect. And so this is an estimator with good behaviors. But there are alternatives. And I mentioned to you, for instance, that if you are interested in the low flows, instead of computing the square of the difference, we could just compute the absolute value. With the absolute value, you avoid compensation between negative and positive errors, but at the same time, you don't put so much weight on the large errors. And what you obtain is a different objective function, which is called sum of the absolute errors. Let me show it to you very simply. And if you scroll down in my web page, I am for now skipping one, which I will get back soon. This is the sum of the absolute errors. Please remember this objective function. You see that they are very simple. And please remember them, because it's not just a matter of being prepared for the exam. The fact is that if you remember the mathematical relationship, it means that you remember the concept. I mean, if you remember the concept, it's automatically, you can write down this mathematical relationship. You don't need to use the same symbols. You just need to learn and memorize that there is a possibility, which is squaring the differences and taking the summation, and there is another possibility, which is taking the absolute value of the differences and then the summation. And this is the sum of the absolute errors. This is not quadratic. We also say that this is an objective function that is not quadratic. And it doesn't have the same nice properties of the sum of squares. This is an estimator which is not necessarily unbiased, but it has the advantage of focusing on the low flows. I mentioned to you that I skip an objective function, which is actually equivalent to least squares. But I want to show it to you because it is basically a transformation of the least square objective function to rescale it in order to have a max value of 1. So let me just say some few words about this. What is the problem? One problem that I didn't mention of the least squares objective function. It gives to you a large number, and this large number, the magnitude of this number, which is the sum of squares, let me go back to it. The magnitude of this number depends on the magnitude of x. If you have the observations that are small values, you get a smaller least square objective function. If the observations are increased in magnitude, then also the magnitude of the least squares increases. So you don't have a possibility to compare different models reproducing different processes. For instance, if I have a model reproducing rainfall and a model reproducing river flow, they give rise to objective functions that are completely different. And if I want in a way to compare the performances of these models, this is something that it's not possible. So the idea that came to researchers was, why don't we rescale this based on the magnitude of x, so that the best performance takes value of 1. So the max is 1. If I get a perfect reproduction, the max is 1. So this gives a way to get a universal comparison. And therefore, how can we rescale it? It is done with the objective function that I skipped here, which is called, it's widely used, so this is why I am introducing it. It's called Nash Efficiency, and it's written N-A-S-H, Nash, from the family name of a scientist who proposed it in 1968. Some references called it Nash-Sutcliffe efficiency, because they were two co-authors of the same paper. Sutcliffe, it's spelled S-U-T-C-L-I-F-F-E. I go to the web page and I show you. Nash-Sutcliffe efficiency. So let me see how we can compute it. Please remember this, learn by memory. You have at the right hand side 1 minus, and then you have a ratio. At the numerator you have least squares. What do you have at the denominator? You have the sum of squares, which is obtained if for any prediction you take the average value, x bar is average value of the x, observed x. I give you some time and then I make some more comments. So first of all, let's suppose that you have a perfect model. Then in the ratio, you have a numerator that is 0, and you get the best performance, which is 1. So this tells you that the rescaling was is done correctly. And what is the lower value, the lower limit of the Nash efficiency? It's minus infinity, because the ratio at the right-hand side, the numerator doesn't have an upper limit. So if the numerator, very wrong model, really bad one, you get the numerator that goes to infinity, and which means that the result of the Nash efficiency is minus infinity. Good. What happens, sorry, before saying what happens, let me spend a few words on why we put at the denominator at the right-hand side, we put this sum of squares, which is obtained by subtracting from any observation the average. So you have a series of observed data, what we call a time series, which depends on time. The x depends on time. You have a series of xt, okay? You compute the average of these observations. You subtract from any observation the average, and you square it, and you take the sum. Why? What is the reason why they thought to use this measure to rescale the sum of squares? First, you understand that this is a rescaling. If you have, I said that the least squares objective function, if you have a large x value, if you have large x values, it increases, but also the denominator increases. So, I mean, by taking the ratio between these two quantities, we rescale it, which is what we wanted to do. But there is something more to say. Let's suppose that you have to make a prediction, you are forced, and you don't have any model. You have just a series of observations. You have the xt, and somebody asks you, what is your best prediction for the next one, for the next future value of x, basing on at least a series of observed values. Without any model, without any information, what would be your best prediction? You would compute the average, wouldn't you? If I am given a series of numbers and I don't have any information, but somebody asks me to make a prediction, I would say, okay, let me take the average and take it as best prediction. So the average value is the best prediction that you would take in absence of any information. So it's a kind of zero information model. Of course, if I have a model, I hope that it gives a better prediction. But this average value is, as I said, as I called it, the best prediction given by a zero information model. So I think it is a reasonable idea to compare the performances of my model with a kind of zero information model. Now, let's suppose that my model is as good as the average. So my model is as good as the zero information model. Of course, I'm not happy. What happens here when I compute the Nash efficiency? That the error given by my model at the numerator is comparable, same order of magnitude, with the error given by the average prediction at the denominator. So the ratio is 1. If they have the same order of magnitude, the ratio becomes 1. And then the Nash efficiency is 0. So a zero value of the Nash efficiency tells you that your model is no better than a simple prediction based on the average. So we are not happy with it, because the model is useless. And if you get negative values, it's even worse. I really throw away the model, and they say that it's hopeless. So of course we are interested in the range 0, 1. If the model is good, the performances are in the range 0, 1. This performance measure is very close to what is called in linear regression the R square. I think that if you had some background in statistics, you heard about the R-square performance measure for the linear regression. This one is very similar. If you didn't hear in your background of the R-square performance measure, let's forget it. I'm just giving this information to you in case you notice that this performance measure is indeed similar to R-square. So the Nash efficiency is useful in our field because if I work on different catchments, I have different order of magnitudes of X. Let's suppose that X is river flow. I mean, the order of magnitude of the river flow for the Po River or a small mountain creek is much different. So if I just compare the sum of squares for the Po River and a small mountain creek, I don't get any meaningful comparison. But if I compare the Nash efficiencies, yes, they are good if they are in the range 0, 1. Let me say that in hydrology and in water resources management, usually we consider a model with a Nash efficiency lower than 0.5 not a good model, not really a really useful model. So I become interested in a model when I see that the Nash efficiency is larger than 0.6. Okay. And sometimes I found models for reproducing even low flows with the Nash efficiency larger than 0.8. Of course, you don't get to 1 because, as I said, we always have uncertainty. So you cannot dream of getting a perfect model. But this is a performance measure that you should know. Okay, now let's forget about these squares. We already mentioned it. And let's go to the next one. The next one is the sum of the relative errors by using the same symbols, or let me say, sum of the absolute relative errors. What does this mean? That you compute the difference observed minus simulated, absolute value, and then any absolute value is divided by the observed value. So you get a relative error. What is the feature? Why should we use this objective function? Because we get even more weight on the low flows. It is easily understandable. I mean, if you have a large X, you divide the error by a large number, and it becomes very small. If you have a small X, let's suppose that X is 0.5, you compute the error in the simulation, and you divide by 0.5, so you double it. You give double weight. So this is interesting for water resources management, because in water resources management, you know we are interested in low flows mainly. On the other hand, you have to be very careful when X approaches to 0, which is something that may happen. You see that if X is 0, an intermittent river, you cannot use this. But even if X is 0.0001, you see that a very small error in the reproduction of a river flow value that is close to 0 is being given a large weight, which is not really nice, because you have to avoid that it's given too much weight to a single value or a small number of values. So this is the reason why this objective function, for instance, is largely used in large catchments. In large catchments, you don't get river flows that are close to 0. It's not used with intermittent catchments. Actually, while I said the Nash efficiency is really widely used, this one is used only in a few cases. But this is not quadratic. The Nash efficiency, keep in mind, is still quadratic, still putting a lot of weights on the large errors. This one is more focused on the low flows. The literature gives you several other alternatives for the computation of objective functions. We don't consider any additional one. I just wanted to mention to you that there are several other possible solutions. And I also would like to mention that you can have some creativity in devising an objective function that is suited for purpose, fit for purpose. You just have to be careful about possible biases, possible, inconsistencies of the objective function that you use if you are creative. You have to check, and you have to check that objective function indeed with increasing information gives to you the result that you are expecting. Which means that you have to be, as I said, you have to be careful. And you may ask me, how can I be careful? Should I look at the theory? Should I look? I would say that we are engineers. We are interested in the technical features of the methods that we use. And therefore, I would just suggest to you that you check with a visual comparison. Once that you obtained the final vector of parameters, once that you succeeded in estimating your model with automatic calibration, make a check with the visual comparison. So in a way, you bridge the two techniques. And with a visual assessment, you can easily get, if from a technical point of view, your result is satisfactory. And I give to you an example, some more consideration to explain to you what it means that we converge to the true value or we don't converge to the true value. What is meant by the true value? So the best, a consistent solution for a parameter optimization is a solution that, as I said, converges to the true value. And the true value means that you make an overall assessment. So you should get good performances in the estimation of high flows and good performances in the estimation of low flows. This is what I mean with true value, consistent solution. If I have a solution that is nice, that works very well for the simulation of low flows, but it's very bad in the simulation of the high flows, the theory wouldn't say that this is a consistent solution. Wouldn't say that, because when I say that a model is good, the theory should tell me that the model is good with a comprehensive assessment of the performances. So it should be good for low flows, it should be good for high flows. If it is perfect for low flows and very bad for the high flows, the theory would say this is not a good solution. But from a technical point of view, for you, it may be the best solution that you want to attain. So your visual comparison is the best way, your visual assessment is the best way to make sure that from a technical point of view, you got the right solution. Maybe that from a theoretical point of view is not the best solution, but from a technical point of view, it's okay. So when I say you have to be careful, the way to be careful is very simple. Make a visual assessment and you can also try to mix the two procedures. If you make a visual assessment and you see that, yeah, it's fine, but let me try with another parameter combination just by trial and error to see if I can improve it. So in a way, you mix the two procedures. And this is a general a general strategy that you should always adopt when you have scarcity of information and when you are responsible for a design. Responsibility means that you should prove, just in case, that you did your best. You did any possible attempt to take the best solution. And any possible attempt means that you consider all the information, all the procedures, and you try to, in a way, to compare them. This is something that I already mentioned to you. When you are in doubt about the goodness of a solution that you adopt, the best way to resolve or at least mitigate your doubts is to compare alternative approaches. And if you get similar results, you're fine. If you get completely different results, then it's not good. And keep in mind that being responsible means exactly this. If you have in front of a court to prove that you did your best, the best way to prove that you did your best is to say, I compared different solutions and I tried all the possible ways to get to target, and this was my strategy. So even here, what I said, run an automatic calibration and then make a visual assessment. It's the best way to compare the two strategies. Okay, now let's see if there are additional considerations that I should make. There is a second large category of approaches. So far what I did, let me go back in the web page. What I did is to focus on calibration through optimization of model performances. But what do you need what is the information that you need to make this calibration? You need data. You need data. You need the X. To compute these objective functions, you need the X. And to make a visual assessment, you need the X. You need the observed values. But what if you don't have any observed value? And this happens quite frequently. You have to calibrate a model, and you don't have observations to compare the simulation with. Okay. If we don't have observations, what should we do? There is a second category of approaches, which is called calibration through expert knowledge. Just 1 second, I run back 1 second because I'm not sure. Okay, the numbers are fine, the numeration is fine. Calibration through expert knowledge. What does this mean? Okay. It means that you have some experience that suggests you that there is a likely value for model parameters. I repeat, it means calibration through expert knowledge. It means that you are using your experience to guess the parameter values. And of course, the question from you now would be, how can I do it? And I give you an example, a very simple example. We discussed the linear reservoir model, and it has only one parameter, and I suggested to you that this parameter is very close to the time of concentration of the basin, which we defined. I gave to you the definition of time of concentration. It's the time that is taken by the rainfall that falls in the farthest point away from the closure to reach the closure section of the catchment. It's the longest way, it's the longest time taken by rainfall to get to the closure section of the catchment. This is the way I defined it. So I said the parameter K of the linear reservoir, you may remember this K parameter is a time constant. You remember the relationship Q flow is given by storage divided by K. And I said our tentative value for K is the time of concentration of the catchment. So if you don't have any observation, you may compute the time of concentration, and there are empirical formulas for computing it, or you may guess it, and then say my guess for K is 4 hours. This works. I mean, it's a possibility. If you don't have data, it's a nice example on how you can use your expert knowledge to guess a parameter value. And don't assume that you don't have expert knowledge. You are an engineer, so you have expert knowledge. You will be an engineer, for sure. So you have expert knowledge. Of course, in order to be able to use your expert knowledge, you have to know the theory. You have to know how a model works. And I gave you the example of the linear reservoir. I think it is a nice example. You have to know how a model works and what is the meaning of the parameter values. And for this reason, we particularly appreciate the models that can associate a meaning to parameter values, a physical meaning. Like, for instance, IMOD. IMOD has a parameter that is Cmax, which is the max storage, max possible water storage in the catchment. It is meaningful. It has a meaning. Also, beta, the parameter beta of IMOD, which regulates the variability of this water storage capacity into the catchment. I show to you some graphs showing what is the progress, the distribution of the storage in the catchment for beta equal to 1, for beta lower than 1, for tending to 0, and for beta tending to infinity. Now you understand why I showed to you these graphs, because I want to give you a perception of what is the meaning of parameter values. Still, you may ask me, but okay, I know that Cmax is the storage, the max storage in the catchment, but how can I estimate it? Still, you may have this question for me. Even if I know, you may ask, even if I know the physical meaning of a parameter, still, it's a problem for me to guess a value, which is true. And the suggestion that I give to you, which is quite obvious, but it is actually very useful, it's look at the parameter values in a similar catchment. And this is possible. Look at the literature. Look at examples of applications of IMOD in other catchments and compare. So you may find that somebody applied IMOD in a catchment that looks similar, same area, same everything. And then let's take these parameter values with the awareness that similarity between catchments is subjected to several considerations, not only the area of the catchment, not only the shape of the catchment, but also land cover, also climate features. But on the other hand, these applications give to you a way for starting thinking about it, thinking about these similarities and how to correct then the parameter values. So you may compare with a catchment that is very similar also in terms of climatic features, etc. But you know that your catchment is more permeable, so you may increase Cmax of something. And then you may also compare the results, like I am in doubt, my Cmax should be 400 or 600 millimeters. Then you run two simulations, and then you look at the features that you want to be better simulated, like, for instance, low flows in our case. And you may see that for the low flows, there is not a big difference between a Cmax of 400 and 600. And then you may say, okay, so if there is no much difference, I don't care about it. This is called sensitivity analysis of the model with respect to parameter values. sensitivity analysis of your results. So if people see that a parameter value is not influential, is not effective in the technical features of my simulation, then we forget about it. We just put a value that is fine to me, and then that's it. This is called sensitivity analysis. Very often it may happen that you have to calibrate a model through expert knowledge, which is fine. Another possibility may be to apply two different models, a simple one, a more complex one, and again compare the output. In any case, remember that when you perform a calibration, you should use all the available information. So if you don't have information, you use your expert knowledge. If you have some data, you use the data, but also don't forget to make a comparison with your expert knowledge. So the result is acceptable to you? Yes, okay, that's fine. Use all the information available for calibration. Okay, let me now get into a different procedure, which is nevertheless still aimed at checking model performances. And this procedure is called validation of the model. Validation is not always possible, but what does it mean, validation? It means that I test the model performances by emulating a real-world application. What do I mean with real-world application? In order to explain what is a real-world application, let's think about what will actually happen when I apply my model in practice. What actually happened is that after estimating the parameters, so after calibrating the model, I apply the model with respect to something that is new. When I apply the model, I'm not reproducing observed data. I am reproducing a new situation, for instance, to predict the future. This is the usual application. I calibrate a model using past data, and then I use the model to predict the future. But when I predict the future, I don't have the observed future. So the real-world application is to simulate unknowns. Calibration is to simulate known values, observed values. Application is to simulate unknowns. And of course, it's more difficult. Because when I simulate something that is known, I can make a comparison. When I simulate something that is unknown, I cannot make a comparison. So it's more difficult. You know that there is a say, and I don't remember who was the person who said that. There is a say that says that the prediction is difficult, especially when it's about the future. Predicting the past is not a big issue. Predicting the future is a big issue. So validation is trying to emulate such a situation where I simulate unknowns. But in validation, I suppose that I have I have the observed values, but I don't use them. If I don't use them, but for a final check. So let me make a more understandable example. Let's suppose that you have 1,000 observations available of the variable that you want to simulate. Instead of using the whole sample of 1,000 for calibration, I use only 800 for calibration. And then I keep 200 in order to validate the model. So I simulate these 200 by assuming that I didn't know them. So I calibrate the model only on the 800, and then I simulate the 200 in order to perform what we call an out-of-sample application or model validation. You understand that the errors that you get are larger than the errors that you get in calibration, because the model is running with respect to something new. Please make an effort to understand the difference between calibration and validation, because this is another question that usually gets students by surprise. Actually, the concept, in my view, is very simple. As I said, you don't use the whole sample of data for calibration. You reserve a part of the sample, which is called, this procedure is also called the split sample procedure for this reason, split sample validation for this reason, because you split the sample. You use a part of the sample for calibration, and the other part of the sample is taken as an out-of-sample validation, which means that you run the model and you compare the model with the observation that you didn't use in calibration. Again, what is validation? You can also say it this way. I ran the model to simulate observations that were not used in calibration. It looks very simple to me, but maybe that I'm not able to convey the concept effectively. And again, this is very often a question that gets students by surprise, which means that when I ask model calibration and validation, the student tells me usually very well what is calibration, but when I ask, but what is validation, then the student is taken by surprise. Okay. I made you an example of validation, which is the split sample. And so you may ask me, what is the part of the sample that I have to keep for validation that I don't have to use in calibration? So if I get this question, there are two answers, two considerations that I would like to make. First consideration, which is important. Keep in mind that when you finally calibrate your model, when you finally estimate the best parameter values, you have to use all the available information. So if you make this experiment of validation, that's fine, but once that you are happy with your model, estimate again, calibrate again your parameter by using everything you have. Okay, so you may say, but in this way I validated a model which is not the same one, the same final one that I get, but no problem for this. So let's make it clear. The final calibration is to be performed by using the full set of data. It would be a mistake if you calibrated the model by using only half of it, and then you apply your model by using only half of it. A judge would ask you, a judge in the court would ask you, why didn't you use all the information that you had available for getting the final calibration? And so this is the first consideration to be made. I hope that you got what I said. This consideration means that you have to calibrate the model twice. One time by using the reduced sample and then validate it, and the final time to use the full sample. Second consideration, when you work with the split sample procedure, with the split sample validation, the percentage of points that you should reserve for validation, so when you split the sample, the size of the calibration sample and validation sample should be evaluated by considering the whole extension. So if you have 100 years of data, like for the Po River, you have river flows for 100 years. then it's fine if you calibrate on 50 years and then you use 50 years for validation, which means that it's a very long validation. But if you have only 1 year of data, it's meaningless that you calibrate the model with a period of less than 1 year. In this case, I would say forget about validation. It's not possible. If you have 10 years of data, I wouldn't tell you 5 and 5. I would tell you 8 and 2. 8 for calibration, 2 for validation. Because calibration needs a minimum period, a minimal period, which is several seasons, at least 5, 6 years. Let me mention, it's not really mentioned here, but let me see. Yeah. It's not really mentioned here. Here I am mentioning the split sample, okay, what I just said. There is a technique that is widely used. It's not mentioned here because I wanted to keep it simple, which is called the Jackknife procedure. And I think it is on the web. Let me check. Jackknife. Jackknife resampling is called in Wikipedia. Let me see if this is what I mean. You see here the Jackknife estimator. I think it is interesting, so this is why, but it's not reported in my web pages, so I will not ask anything at the exam. The Jackknife estimator of a parameter is found by systematically leaving out each observation from a data set and calculating the parameter estimate over the remaining observation, and then aggregating this calculation. So what is done, for instance, in hydrology, let's suppose that you have 10 years of data. You systematically leave out 1 year for validation, and you perform a calibration 10 times by leaving out each time 1 year. And then you validate the model on the year that you have left out. And so you get 10 validations. And this is what is called the Jackknife validation. In this case, they say that you leave out only 1 observation. In our case, it's not meaningful to leave out only 1 observation because we have a seasonal cycle. And therefore, I would say that the minimum that you have to leave out is, when you deal with time series, is 1 year. But if you have 10 years of data, as I said, you may perform calibration 10 times, and you leave out each time 1 year. And then you get 10 parameter estimates, and you compare them. If they look similar, you are happy. If they look much different, it means that there is a lot of uncertainty. And you have 10 results of validation. This is the Jackknife estimation. It's also called leave one out estimation. Okay. Our final consideration, I mentioned creativity, which is indeed something that you have to use when you work with environmental processes and models. You have to be creative. You have to try to get an interpretation of your results. You have to really make considerations on the reliability of your model. You don't have to take the model as a perfect one. You don't have to trust the model without a very careful scrutiny. You have to really scrutinize your results. when you try to reproduce environmental processes of any kind, there is, and I told you several times, uncertainty. Don't assume that models are a perfect reproduction of reality. Today, there is an increasing interest for what are called digital twins of the Earth system. So we are trying to reproduce the Earth system with computers by using analytical models, which is perfect. It is a very interesting idea. And this idea was further promoted after the pandemics, because the pandemics gave a strong support to the use of digital technologies, which is very fine, very good. In these 2 years, we had really a giant leap forward, a big step forward. And so, I mean, this is very good on the one hand. On the other hand, there is the risk that this idea of creating a digital twin, there is the risk that this idea gives too much support to our faith in analytical model, our belief that these models are correct. We don't have to assume that these models are perfect. These models are very useful, but they are uncertain. We cannot make predictions of environmental processes in the very long future. This is not possible. We can make predictions, but there is uncertainty. So my recommendation for you is, given that you are responsible, you are an engineer, you are responsible for your design, make a careful scrutiny of the results. Very careful scrutiny. Validation is essential. And you will see several times that you are proposed modeling results that are not validated. You have to be very skeptical about the use in engineering of models that are not validated. One different thing is science, research. I mean, a model is also useful because it gives indications under certain assumptions. Even if they are not validated, models may be useful. But in engineering, you have to be very careful with models that are not validated. What we want is models that don't fail in engineering. When we make predictions in engineering, we cannot tolerate a relevant risk of failure. We are responsible for it. So let's make really a big difference between engineering, which is needed, because when you are at the end of the story, when you have to solve problems, you need engineering. And let's make a big difference between what is research and what is technical design. I am lucky that I had the opportunity and still I have the opportunity of doing both of them. And I can tell you that my attitude is completely different. My approach is completely different. One thing is writing a paper, another thing is put my signature under a technical design of a bridge or a levee or something like that. So I really hope that you are aware of this. Now, while I was closing the page, I realized that there is indeed a link to Jackknife, which is also called cross-validation, and it's a link to another Wikipedia page. But it is more or less saying the same thing. You see, cross-validation, sometimes called rotation estimation or out-of-sample testing. Okay. But again, this is something that usually I don't ask at the exam. It's just a link, so you know that how to have to use links in my web pages. Okay, fine. Any question about this? Good. Let me go back to our main page and let me check. Okay, I think we can go to the next one, but before going to the next one, you see here design of river barrages. Let me make a premise. And the approach that I use in this subject, in teaching this subject, as you have seen, is an approach that is basically based on the objective of giving to you the latest possible information, the latest possible scientific information. So my approach is quite scientific. I mean, if we look at the list of my lectures, there is sustainable management of water resources, which is a relatively recent concept. Assessing water resources availability, inductive methods, I try to give to you an overview of the recent outcomes from the literature, and for deductive methods, the same thing. You have seen that I discussed the IMOB model, and I said it was proposed in 2000, so it's just 20 years ago. The linear reservoir was more, it's a longer history, but still it's a model that is used in advanced applications. And then when I talked about model calibration and validation, groundwater models, my focus has always been on the recent developments. So it's an approach that I would say it's scientific, theoretical. And, but within this approach, I was careful to emphasize what is the difference between, like I did just now, science and engineering. So what are the approach, what are what is the approach that you have to take when you pass from application of the theory to technical design? What is the approach that you have to take when you enter into the phase of technology transfer, of knowledge transfer to technology? In order to make sure that my approach is really comprehensive in this respect, I now would like to introduce a purely technical topic, which is more related to technical design. We are not making any technical project, any design project in this subject, but I would like to give to you an example which is strictly connected to sustainability of water resources uses. And it's this example, I decided to focus it on the design of river barrages. River barrages, what are river barrages? River barrages are transversal barrages with respect to the longitudinal direction of the river flow, which are realized in order to for different purposes, but in water resources management, they are frequently used in order to withdraw water. So we build in water resources management a transversal barrage, a river barrage, in order to withdraw water. And why do we need a barrage to withdraw water? For the very simple reason that in order to withdraw water, we need to collect some water in a specific place. We had to slow down the velocity of the flow in order to create a basin, a small pool, at least a small pool. The pool and the basin may be larger because a dam is still a transversal barrage, even if we wouldn't define it as a river barrage. The river barrage usually creates, as we will see, a small pool upstream. But in any case, we need to create a reserve of water. And what is the purpose? The purpose is that, first of all, if we create a reserve of water, we can, in a way, compensate the shift between river flow and water demand. So when I need more water than the river flow, when the flow of water that I need to take from the river is higher than the river flow, I can compensate only if I have an accumulation. And this is typically the case because your river flow is the same during night and during day, but during the day you get water, during night not, usually. So with a small basin or with a basin, you compensate these shifts. And there is also the need of stabilizing the water level. If you want to take water, you need to stabilize the water level. Whatever system you use to take water, it's much easier if you stabilize the water level. If the water level is changing continuously, then it's a problem to get water. You know, even if you go with tanks in order to get the water, if you have changes in the water level, it becomes more difficult. So it is easier to take water from a lake than from a river, because the lake is calm water, the level is stable, etc. And the lake is a large storage. So for this reason, we build the river barrage. Let me look at some pictures of river barrages. Let me look on the web. It's easier. I search first in Italian and then in English. In Italian is traversa fluviale. Let's look at the images. So you see a panorama of several river barrages. Some pictures are from my website. So let me, for instance, look at this. 1 second. This is not a very clear picture, but you can see a barrage. And upstream, you have a small reservoir that I mentioned to you. This is not a dam, it's not an artificial reservoir. It's just a small basin that is created by a barrage. And the picture is not very clear, so let me look at something different. This one is still not very, no, this one is clearer. Just 1 second. Clearer, but not very much, but still okay, it's okay. This is a barrage that is located at the downstream limit of one big lake that is located in Italy, which is Lago di Seo. And in Italy, there are some big lakes in let's say, at the boundary between the Padana Plain, which is the huge plain in the north of Italy where Bologna is located. At the boundary with the Alpine region in the north, there are some big lakes. These big lakes were created by big glaciers during the last glaciation. And the glaciers basically reached the plain, and at the end of these glaciers, once the glaciers retired, they left these huge excavations that were filled by water. So there are several big lakes, which are Lago Maggiore, Lago di Garda, Lago di Seo, Lago di Como, and they are very large indeed. And the largest lake in Italy is Lago di Garda. All of these lakes now are regulated, which means that at their lower limit, humans built barrages in order to be able to regulate the lake level. And the reason is that they wanted to be able to store water during the rainy season in the lake to be released downstream during the dry season for irrigation purposes. And when they release this water for irrigation, usually they also use the water energy to produce hydropower, okay, because they turbine the water once it is released, so in order to produce hydropower. This is the barrage at the closure of Lago di Seo, and let me see some other example. This is another barrage, but again, this is not very clear, and that is created in order to originate a pool upstream. And here is another one. Let's see if this one is a bit larger. Yes. This is a barrage that is located at Sarnico in Italy. And again, you see that there is this transversal infrastructure which creates upstream a pool. All of these barrages are regulated, which means that what they are called mobile barrages, which means that they have the possibility with through some tools to regulate the river level upstream. There are in other simple structures, there is a different category of structures that don't allow any regulation. They are simpler, and they don't have moving gates that allow to regulate the level upstream. Let me see if I can see some more pictures. This is a detail of another barrage. It's not very clear, the picture, but you see that there are these tools that allow you to, in a way, to close also the downstream flow in order to store water. These are tools like gates that allow you to regulate the upstream water level. Okay. Okay, I think we can move back to my web page. Design of river barrages. Sorry. Now, river barrages are one purpose for which they are created, they are built up, is water withdrawal, as I said, but they are also used for hydropower generation. And are also used in some cases just in order to stabilize the riverbed, to create a fixed point in terms of elevation of the riverbed. So we actually, in English, we use the term river barrages also for identifying this type of structures, which are also called in English check dams. When the purpose is only to stabilize the riverbed, they are also called check dams. But in English, with the term river barrages, usually we mean these three categories of structures for hydropower generation, for water withdrawal, and also for stabilization of the riverbed. In Italian, they are called traverse fluviali, and in Italian, traverse fluviali doesn't include any structure for the stabilization of the riverbed. They are called briglie. But in English, river barrages sometimes are also used with this purpose. And let's focus on the purpose of water withdrawal. The purposes can be combined. So very often you have barrages that are used for water withdrawal that is combined with hydropower generation. They can be combined, but let's focus on barrages for water withdrawals. And according to the Italian regulation, we can identify 4 categories of transversal structures that are built over rivers. And these transversal structures can be divided in the category of concrete or stone masonry dams, so dam, earth dams, other type of dams, and then river barrages. So on the one hand, we have 3 categories of dams, and at the end of the story, an additional category, river barrages. What is the difference between a barrage and a dam? I already mentioned it. The difference is the size of the upstream reservoir created by the barrage. Dams usually originate a large reservoir upstream. How large? The Italian regulation defines the boundary between barrages and dams, and the boundary is defined according to 2 criteria. One is the volume of the reservoir, which should be for dams larger than 1 million cubic meters of water. If the upstream barrage is more than 1 million, it's a dam, according to the Italian law, Italian legislation. But there is a second criteria. and it suffices that one of the two is satisfied in order to identify a dam. The second criteria is the height of the barrage with respect to the undisturbed riverbed. If you have a height of more than 15 meters, it's a dam. As I said, it suffices one of the two. So if you have a depth of more than 15 meters, an height, sorry, of more than 15 meters is a dam. If you have an upstream reservoir more than 1 million is a dam. It makes a big difference because from the point of view of legislation, if you design a dam, you have to make many more additional checks on your design project. And the design project is to be checked by the national government, while a barrage is checked only by the regional government. This is extremely important to keep in mind, because your duties for designing dams are much more articulated with respect to designing barrages. Of course, if you go in a different country, you may have different criteria for the identification of dams, and you have to be informed on that. Even if the criteria are, there is an international organism for which gives technical guidelines for the design of dams, which makes sure that the criteria is not very dishomogeneous between different countries. So the indications that I gave to you more or less will be the same in different countries, but there might be differences on how you measure the upstream reservoir and the height. So, for instance, I told you that the height is to be measured with respect to the undisturbed riverbed, and you measure the elevation of the highest possible discharge, the highest possible weir. Weir is the threshold over which you have a flow of water. So you get undisturbed riverbed, highest possible elevation of the barrage that is surmounted by water, and you measure in this way. In other countries, you may find legislation that tells you to measure from the depth of the foundation. And this was what we previously used in Italy, but then we changed it because it's more objective to measure from the undisturbed riverbed. Okay. So you have these categories. We don't focus on dams, we focus on barrages. And you see that here we have a definition. A river barrage is a low-head diversion dam that is built to allow diversion of a part of the river flow. Let me check if the link is still working, because I didn't check it recently. Yes, but this is defining, a barrage is, here you see it. This is anticipating something that I am mentioning to you later. So here, for instance, it says that a barrage consists of a number of large gates that can be opened, actually, or closed, to control the amount of water passing through. Actually, this is not always required. I mean, this possibility to open or close gates to regulate the water flow, it's a possibility, but it's not required. As I mentioned to you, there might be what we call fixed barrages without gates. They just fix a limit to the elevation of the bed. They originate some water storage upstream, but without gates. So it's just a wall emerging from the riverbed that is retaining part of the flow upstream. Of course, if you don't have gates, you don't have the possibility to regulate the upstream level. If you don't have gates, if you get a lot of flow into the river, you get a high water level. If the flow decreases, the water level decreases. Gates allow you to regulate the downstream flow in order to keep the water level constant. Of course, it is nice to keep the water level upstream constant, but it's an additional complication. So in some cases, we prefer not to have gates because gates need to be opened, closed, surveilled. So sometimes we prefer simple structures. In fact, I am mentioning here a classification of barrages, which it's not found on the Wikipedia page that I showed you before. Regulated barrages, which are equipped with machineries like gates or regulated sluiceways to keep the upstream water level stable. If you don't know what is a sluiceway, I will show you a picture in a moment. Unregulated barrages, when regulation of the upstream water level is not possible. Here there is a third category which we don't discuss, temporary barrages. Temporary barrages are often built by people during the summer when they need to take water. Usually people need to take water for irrigation or for other uses, but still it's typically a requirement for summer, not for winter. If it is irrigation, for obvious reasons, but also for other uses. Usually during winter, you have more water available. You don't need to get the water from a river. You may get the water from small ditches, and you don't need real heat. But during summer, when there is a shortage of water, you may need to take water from rivers. And so people sometimes build temporary barrages by using stones, stones mixed with soil, with earth. And so these temporary barrages, which are very simple to build up, they have the problem that at the first high flow, they are wiped away. But this is not a big problem because the first high flow usually is in the fall season, and therefore they don't need water anymore. So the temporary barrages are just built for a few months and very low cost and are frequently used. But we don't discuss them because usually they don't need a technical design. Just keep in mind that even any time that you get water from a river, you should ask for a permission because water is a public good. And you are not allowed to take water without letting the administration know. And temporary barrages, are very easy to be built, and it happens quite frequently that people don't ask for permission because in many cases, the water withdrawal is so reduced that they feel like it's something that doesn't have any impact. But if you are consulted as an engineer, you should let people know that this is not allowed. And as I said, any withdrawal of water needs to be communicated. Even when you get water from the mountains, maybe from springs. There are some people that, for instance, they connect their house to springs. This needs to be communicated. It's not something that it's allowed because, as I said, water is a public good. The management of water may be taken by private companies, but still they need permission because, as I said, water is a public good. In Italy, but also in many countries, in almost all of the countries of the world. Now, we will focus on unregulated barrages. Why? Because we don't have much time to dedicate to this topic. And also, unregulated barrages are the type of structures that you may be asked to design at the beginning of your career because they are simple. So I prefer to teach, when I go into technical design, I prefer to teach, to start teaching from the simple infrastructures because these are, as I said, the type of technical design that you may be asked to take care of at the beginning of your career, because complicated structures, if you are involved, maybe that you are involved in the design of complicated structure, it's a nice opportunity, but if you are involved, usually you are involved with a teamwork. Simple things are those that are more demanding at the beginning of the career, because you may be involved alone, and even if they are simple, they entail responsibility and they require some knowledge and some care. Before moving to the discussion of unregulated barrages, I just would like to show you this map, which is embedded in my webpage from Google Maps. And it's an aerial view of a big regulated barrage on the Danube. And it is, the Danube is here setting the boundary between, I don't remember which countries, I think between Austria and let me see. It's between Austria and Germany, maybe. I don't know. Anyway.
No, it splits two cities, bro.
Sorry?
It splits two cities.
Okay. Let me see, because I went off. Just in order to solve this doubt, let me.
Yeah, Austria.
Okay. Mm-hmm. Yeah, correct. Two regions then. Yeah. Mm-hmm. Okay. Anyway, it is setting the boundary between two administrations. So this is the reason why they made it symmetric. You see that there are two. If you look at the structure here, it's symmetric. There are gates in the middle which allow for regulation, and then there are two hydropower stations on the embankments, which close to the levees, which I think they were built for a reason of symmetry, because in order to give the possibility to share the hydropower generation between the two administrations. And also here you see the navigation pool, which allows water to pass by. The problem with these barrages, when they are built on large rivers, is that they slow the flow down, and they isolate, from an ecological point of view, isolate the downstream part from the upstream part. And therefore, the result is that the water quality is deteriorated a lot. This is a problem that they have on the Danube, but not only on the Danube, on several rivers, big rivers in Europe and the United States. And this is the reason why along the Po River, we were not allowed to build more than one barrage, which is at Isola Serafini, because water quality that is deteriorated a lot. But anyway, this is a nice possibility and opportunity to zoom in and out and see. And also you see on the web, there are also pictures if you look on the web for this barrage. This is a nice example. Okay, I think that now we can make a break, and then we will focus on the next hour on unregulated barrages. Okay, so let's go into the details now of unregulated barrages, and let's look into the details of the technical design. First of all, unregulated barrages are often built on small mountain rivers, and the reason is that they are simple structures which are usually placed on in remote locations. And the reason is that in mountain areas and for the purpose of taking water from mountain rivers, usually we don't need large infrastructures. Of course, if you want to build a barrage on the River Danube, then the structure is a large infrastructure which requires an investment of resources that is correspondingly large. For mountain rivers, the structures have low dimensions, low size. The resources required and available are much more reduced, and for this reason we prefer to use simple structures which don't need any remote surveillance, any regulation. These structures are located in mountain areas, which implies that you may have also accessibility that is limited. And also for this reason, we prefer to use structures that require the limited maintenance. The purpose which we focus on is water withdrawal which may be carried out, may be realized for the purpose of hydropower generation or water use. As I said, sometimes we can combine the two uses. The first problem is that we need to resolve from a technical point of view is the estimation of the design flow. So what is the max water flow that we want to be able to take from the river? This is determined by evaluating water demands and water availability. We already discussed what is the technical procedure that we follow in order to assess water resources availability. So we don't focus on it. Basically, it's the flow duration curve that we evaluate. And here there is a discussion on the flow duration curve again, which is basically taken by the web page that you already know, which we already considered. There is a discussion of the two indexes which we use and we already discussed in order to quantify the impact of water withdrawal. So we don't focus on this. I would like to focus now on the structure and the solution of some technical challenges which we have to solve in order to design the barrage. So the structure of unregulated barrages. First, let me have a look at the figure here. And let me open the figure in another page. Here it is. This is a typical structure of an unregulated water barrage. There might be alternatives, but this is a I think it is a meaningful scheme which is devised in order to limit the transversal size of the intervention, of the structure. You see that the structure is mainly elongated along the longitudinal direction, where with longitudinal I mean the direction, the main direction of the river flow. The direction which is highlighted by the ondulated arrow on the left. So, as I said, this shape is particularly appropriate when you have a small room on the sides, on the hill slopes. So you have a small room in the transversal direction. So here the solution is to elongate the structure in the longitudinal direction, because typically this is the situation that we have in mountains. The slopes are very steep, and therefore we cannot use large structures. We have to use the room that is already available in the riverbed. But there are some other layouts which are more developed in the transversal direction. Of course, it depends on the context. But let's focus on this one, because the main elements that we need to discuss, the main components of the structure, are all present here. So we have the transversal barrage, which is fixed at two longitudinal walls. Typically, this is not strictly required. If the sides, if the hill slopes are very stable, like rocky hill slopes, you can just fix the transversal barrage to the hill slopes without any need for longitudinal walls. But if, as it often happens, you need to stabilize the hill slopes, then the longitudinal walls may be required. The need to stabilize the hill slopes is particularly important when you have a small space into the riverbed, and therefore, in order to include your structure into it, you need to dig a little bit the foot of the hill slopes. You need to remove the foot of the hill slopes, and then, in this case, in order to avoid landslides, you need to stabilize the foot with these longitudinal walls. The transversal barrage has the central part that has lower elevation usually. And this is what is indicated here with the arrow main spillway. This is a part that is located, has lower elevation, while the sides of the transversal barrage have higher elevation. Basically, the parts that you see that are signed with this group of parallel lines are sloped in the transversal direction. And what is the reason why we want to keep the central part at a lower elevation? The reason is that we want to keep the main flow far from the hill slopes. We want to concentrate the main flow in the center of the riverbed to avoid erosion at the foot of the hill slopes. Even if you have transversal longitudinal walls, it may happen that these walls are damaged by the flow, or it may be that these walls are overtopped. And in this case, you want to avoid high flow velocity against the hill slope in order to limit erosion. And if you concentrate the main flow in the center of the riverbed, you mitigate this type of problem. You see on the right side of right with the shoulders to upstream. On the right side, there is another spillway. This spillway is located at a lower elevation with respect to the main spillway, and it's the spillway of the environmental flow. It's the spillway with the lower elevation. Okay. Just let me make sure that you have a full knowledge of what is a weir, what is a spillway. Spillway and weir are synonyms. So if you look at this figure here, the flow is passing over a spillway. And when the spillway is, because it's a way through which the water spills, okay? When the spillway has a large extension in the longitudinal direction, so it's a large spillway, we call it also weir, okay? I forgot to mention the sluiceway, what is? So let me check what is the best figure to show it, but I think this one. These are sluiceways, so the water passes through, and the sluiceways are often just placed, their bottom is coincident with the riverbed. Okay, so the water doesn't pass over, it would be a spillway. These are sluiceways, okay? And another, let me check. I think there is a nice figure of a sluiceway that I know well. Okay, here is a transversal river barrage which is placed close by here. Let me see if I can enlarge it a little bit. And you can see the sluiceways here. These are typical sluiceways. So this barrage can be overtopped, so you have a weir in the top, but there are also sluiceways that allow the low flow to pass by without overtopping. So basically you have overtopping only when upstream you have an increase of river flow. And also you see that there are these dissipators of energy, which are structures that allow to dissipate the energy out of the sluiceways, because when you have the water level increasing upstream, then you have the water passing through the sluiceways that is coming out from the sluiceways themselves with a lot of energy. And then you need to dissipate the energy in order to avoid erosion. Okay, so I think we clarified what are the technical terms. Here you see a picture of the same barrage with a lot of water flow, with a high water flow coming. So you see that upstream you have a retention of water, and downstream you have the water coming out from the sluiceways, and you see the turbulence originated by also the presence of the dissipators. Okay. So let's come back to here. So, as I said, the environmental flow spillway is the spillway through which the environmental flow passes through. And it's located at a lower elevation with respect to the main spillway. Why? Because when you decide the elevation of a spillway, you basically decide the priority. So if you put a spillway at lower elevation, you give higher priority with respect to a spillway located at a higher elevation. What do I mean with priority? I mean the timing. I mean that if you put a spillway at a lower elevation, there is a preference for water to pass through the spillway with the lower elevation. So you give it a higher priority. And the water goes first, this is why I mentioned timing, to the spillway with lower elevation, and then if there is a lot of water available, then maybe the spillway with a higher elevation. So elevation of the spillways is a mean to define their priority. So given that we give priority to the environmental flow, because the environmental flow is the first one that I have to ensure passes through the spillway, through the barrage, then the spillway of the environmental flow is the one with the lowest elevation. And here in this scheme, the environmental flow spillway is placed just side by side with the main spillway, okay? But it's a lower elevation. You can see the elevation here, but we will discuss with more detail later on. These spillways don't have any gate, any closing gate on them. The environmental flow spillway cannot be closed. So usually the administration doesn't allow you to put any gate there. And the main spillway is the spillway through which you have the transit, the passing by of flood flows, and therefore no gates, because you don't have to interfere with the flood flows, okay? Now, let's talk about water diversion. How do we take water from this structure? Through what is called diversion spillway, and you see two of them here on the side. So here, water diversion is done through the side walls. This is an advantage because by withdrawing water along the longitudinal direction, you minimize the chance of getting floating material. Floating material is passing by in the longitudinal direction. So if you place the diversion spillway in the same direction, then you minimize the chance of diverting trees, etc., floating material, and also garbage or etc. The diversion spillway is usually equipped with a gate, which can be remotely controlled, just in order to be able to close the diversion if something happens. Like, for instance, during floods, we often close the diversion. Why? Because during floods, we have a lot of turbidity in water, and we don't want to take water with a lot of turbidity. So it is usual practice that when the river flow exceeds a given threshold, we close the diversion spillways. Very good. And then the diverted water gets into a sequence of side structures. First, we have a gravel trap, which has the purpose of removing the gravel that eventually may be transported by the water that we divert, the water that we withdraw. Gravel is defined as loose material transported by the current with larger diameter, and therefore it's the easiest to remove. When you have to remove suspended material with small dimension, with small size, or colloids, these are more difficult to remove. So we decide usually to separate the removal of the largest diameter material from the removal of the finer material. And therefore we first put there a gravel trap in order to remove the gravel, and we separate with a step a subsequent pool where we remove the sand. So it's better to, as I said, to divide the removal in several different pools, and this is for the sake of an easier cleaning, an easier maintenance. In order to clean these pools, you need a bottom discharge, which is called here flushing sluiceways. The flushing sluiceways are protected by gates, are closed by gates, and they are sluiceways, so they are put on the bottom of these pools, and when you remove the gate, when you raise the gate, of course you have the flush of water through the sluiceway, and hopefully this flush of water with this water flow with high energy will remove the gravel that was accumulated in the gravel trap. Sometimes the flush of water is not enough, and then we have to intervene manually to clean the gravel trap. And this is done periodically, and it's done by closing the diversion spillways and then opening the sluiceways, and then maybe manually intervening in order to remove the loose material. As I said, we have a step dividing the gravel trap from the sand trap. The sand trap may be divided in two chambers, like here, in two channels, for the reason of an easier cleaning and easier maintenance, because so you can clean them in turn. And you first clean one, and you keep the second one operating, and so forth. Of course, the same solution may be used for the gravel trap. And the reason why it is pictured here only for the sand trap is that the removal of sand is more complicated than the removal of gravel, and usually takes more time. So the removal of gravel usually is very quick. It's just flushing water and then maybe intervening with manually with an excavator, with a mechanical tool in order to remove it, but it's easier. Instead, the sand trap is more complicated because it is collecting material that may be cohesive, and therefore cleaning is more difficult. In the sand trap, I also put a top spillway, which is conceived in order to evacuate the excess flow that may be withdrawn from the river. So it may be that you forget to close the gate, and then you have an excess flow coming through the diversion spillways, and you need to evacuate this excess flow immediately back into the riverbed, because we may not be in the condition of withdrawing it, because these structures have a design flow, a max flow that can be withdrawn. If the diverted flow is greater than the max flow, then you need to evacuate the excess flow. Also, you see that there are flushing sluiceways also for the sand trap. And then usually the water that flows through the sand trap passes over another step. The step is needed in order to keep the sand, the accumulated sand, upstream. And then there is an upstream tank, which is the final pool. What is the purpose of the upstream tank? Usually the purpose of the upstream tank is just to make sure that the pipe to the water system, the pipe that brings water downstream, is covered by a sufficient layer of water. I try to explain better. The top of the pipe, the roof of the pipe, should be always covered by some water in order to avoid that we get air into the pipe, because air into the pipe is highly damaging. When you have a pipe bringing water downstream, you have to absolutely avoid that you have higher bubbles that are transported into the pipe, because the mix between water, which is high pressured water, and air bubble, it's highly damaging, because you have some continuous turbulence that is originated by the displacement of the bubbles of air, and usually they tend to displace at the roof of the pipe, but then the pressure of the water can move these bubbles around, and you have a continuous displacement of these bubbles, which originates continuous hits of water against the walls of the pipe, and this is absolutely to be avoided. So you don't want water, air into the pipe, and the way to avoid it is to make sure that the roof of the pipe is covered by a sufficient layer of water. And this is the purpose of the upstream tank, to make sure that you have a tank which is always full, and the pipe is in the bottom of the tank, so you don't have any air entering into it. Another issue that I want to mention here is the presence downstream, the transversal barrage of protections against erosion. And they may be boulders, they may be other forms of protections, they may be like concrete floors or concrete basements. And in any case, you need some kind of protection because the flow through the main spillway, once that the flow reaches the bed downstream, the river bed downstream causes erosion. And this erosion is to be avoided because it's at the foot of the barrage. And if you have an excessive erosion at the foot of the barrage, then the barrage can be ruined downstream by the pressure of the water combined with the erosion of the foot. Okay, so this is what we have to design, and we can identify here some challenges in terms of design. First, the design flow, but we know how to deal with it. So on the one hand, we have to study water demands, we said. On the other hand, we have to study the flow duration curve, and through a mix of these two these two types of information, you get the optimal design flow, which is fine. We know how to do that. A second challenge is the location in terms of elevation of environmental flow spillway. In order of elevation, it's the lowest one. And then we have to give priority to what? To the diversion, because after we gave priority to the environmental flow, we have to give priority to the diversion. So in terms of elevation, the next one after the environmental flow spillway is the diversion spillway. And then the highest one is, as we said, the main spillway. After we gave priority to environmental flow and to diverted flow, then we have to make sure that the excess flow, besides environmental flow plus diverted flow, the excess with respect to this sum is delivered downstream through the main spillway. But these elevations have to be defined quantitatively. So I have to say, what is the elevation of the environmental flow spillway? What is the elevation of the diversion spillway? What is the elevation of the main spillway? In order to define these priorities. This is another challenge. Another challenge is sizing the gravel trap and the sand trap. What is the size of these pools in terms of volume of water that they can collect, in terms of velocity of the flow within these traps? Because, of course, I have to make sure that the velocity is low. I have to avoid turbulence if I want sediments settling down. Another challenge is what is the elevation of the bottom of the upstream tank. If I want to make sure that the roof of the pipe is covered by enough water, what is the elevation? What is the elevation of the bottom of the upstream tank? These are what we call hydraulic question marks, hydraulic design. And then there are question marks related to structural design, which we will not discuss. So I'm not estimating forces against this structure given by the pressure of water or the pressure of soil. I'm not estimating these forcings because these are related to structural design, which I don't want to discuss here. But I want to discuss a little bit what are the questions related to the hydraulic design. Okay, so let's keep in mind this scheme, and now let's focus on the questions that I mentioned to you. And first, let me talk about the elevation of the sluiceways, of the spillways. What I said is that the environmental flow spillway is the lowest. So what is its elevation? Let's keep in mind that it's the lowest one. What is its elevation? Okay, so given that this is the lowest spillway, it is what regulates the upstream water level. Meaning that, let's suppose that you have a small flow into the river. Of course, if you have the flow tending to zero, the upstream water level tends to the lowest, tends to the elevation of the lowest spillway. So the environmental flow spillway is what regulates the minimum water level upstream. And then if you have river flow increasing, the water level upstream will increase, of course. This is an unregulated barrage. So again, let's suppose you have zero flow into the river, the water level upstream will become the same of the elevation of the environmental flow spillway. It's a pool with the same elevation. And then, given that the barrage is unregulated, if you put some river flow entering from upstream, you have an increase of the water level. It's unregulated. So the higher the river flow, the higher the water level. Okay, because this is what happens through a spillway. If you want water passing through the spillway, you need excess elevation of water with respect to the spillway. And if you want to increase the flow through the spillway, you have to increase this excess of water. There is a relationship that we will see in a moment between excess of elevation upstream and the river flow through the spillway. So this is the first concept that you have to fix in your mind. Okay? Unregulated barrage, you have a flow through the barrage which is proportional to the difference in elevation between the spillway and the water level. So increasing river flow from upstream, increasing elevation upstream. So let's go back to the question. What is the elevation of the environmental flow spillway? I have to decide what is the elevation, the minimum elevation of water level that I want upstream. And this gives the elevation of the environmental flow spillway. Fine. So let me make a drawing on the blackboard because I want this concept to be clear. Okay, now I move so you can see from on the blackboard. Let me share the screen. Okay. So let's suppose that we have a river bed, and here we have a barrage. And I only depict the elevation of the environmental flow spillway. Environmental flow spillway. Okay, good. And let's suppose first that Q is equal to 0. Q is upstream flow. Okay, perfect. If you don't have any flow from upstream, you get a water level that is equivalent to the elevation of the environmental flow spillway. Perfect. I think this is clear. And in this case, this is a static situation, Q equal to 0, which usually doesn't happen in practice, which means that you don't have any river flow going downstream, which is fine, because if you don't have any river flow from upstream, then you can't release any environmental flow. It's a natural situation. I mean, it's not a problem. And of course, you cannot withdraw any flow. Because if you don't release environmental flow downstream, you cannot take any flow. Okay. Now, let's suppose that Q becomes greater than 0. What happens here? You have an increase of river level upstream, because when you have some water coming, of course you have an increase of the river level. And then you get more or less here. And then here you have some flow that goes down. Perfect. But this flow can be Q less than Q dmV. Q dmV is the environmental flow. Still less. So, what is the consequence? No withdrawal. No withdrawal. Okay, good. Now, let's suppose that Q upstream is much larger than 0. It's increasing. Okay, good. Now we get a situation like this one. Here you have Q equal to Q dmV. For instance, if I select properly the level, I get to a situation where Q is equal to Q dmV. And here, the consequence is that you can start withdrawal. I mean, once that downstream I have the environmental flow, I can start withdrawal. Then, this is precisely the elevation of withdrawal spillway Is it clear, the concept to you? I mean, once that you get a water level such that downstream through the environmental flow spillway, you have precisely the environmental flow, you can start withdrawal, which means that you have to displace your withdrawal spillway precisely at this water elevation. This is an automatic way, without regulation, of making sure that you start withdrawing water when you have satisfied the environmental flow downstream. Without regulation, this is an automatic way of reaching your target. The elevation of the withdrawal spillway must be placed at the elevation of the water level in the reservoir that corresponds to the release of the environmental flow downstream. So what do I need to make sure that this happens? If I indicate with the symbol, let me just extrapolate it here, delta H2. The difference in elevation between environmental flow spillway and the water level that I just determined, I need a relationship to compute delta H2. You understand that this relationship must be a relationship of the type delta H2 equal to function, some function of Q dmV. This picture here clarifies that it's Q dmV which dictates delta H2. So I need this relationship here. What kind of relationship is this? It's a relationship from fluid mechanics that allows me to estimate the flow through a spillway. This is flow through spillway. Flow through spillway. It comes from fluid mechanics. We don't go into the details now. I will start on Thursday by giving an analytical relationship for this relationship here. Analytical form for this relationship here. I hope this sketch helped you to understand how it works. This is, in principle, very simple once that you got it. But my experience suggests to me that this is another of those things which it's not immediately easy to understand, especially if you don't have a strong background in fluid mechanics. So this is why I want to stop here, for giving to you the opportunity to reflect on this scheme before Thursday. It is very simple. I mean, if you start from a situation where you don't have any flow, and then you increase the flow upstream, you understand that it's the flow upstream that conditions the water level through the passing by over the spillway. Okay, I prefer, as I said, to stop here, and then I'll see you on Thursday. Thanks everybody who is connected remotely. And again, if you have any question, please step in.